as you get into the second part of this section, there's this one section in the textbook, and I don't want you to write this down. There's one section in the textbook that talks about how when we start working with the variables with this, how you can wind up with absolute values. This can get extraordinarily messy because when you have if you're taking an nth root of something and the n value of the root is even and the value inside that you're taking of it is also even. So if you have a fourth root of x to the eighth, that kind of thing, you would wind up with absolute values for your answers because your distances will always have to be positive when you start walking through these things. What they do that with this section, and for most sections in Algebra 2, and I think when you see this again in pre-calc, a lot of times what they will state is that assume all variables being positive. So you don't have to worry about this scenario. What I'm getting at here is as you go through, and if you're simplifying out radicals with variables and the nth roots and stuff like that, you don't have to worry about this absolute value trick that does show up. Answers in the textbook don't show it. They just let you know that it is a possibility because if I take the fourth root of 5 to the fourth, I could take the fourth root of negative 5 to the fourth. Because if it's in parentheses, it all cancels itself out. So that's why that absolute value does occur. So don't worry about it. I know that the textbook talks about this. I know pre-calc textbooks talk about this. It's just one of those things just to let you know that I'm always going to say assume that all variables are positive so you don't have to worry about that. Okay? It's just when you see all that, you see a lot of weirdness, if you see absolute values thrown in, just remember I'm just always going to say assume everything's positive. Yay. Anyway, so what we're going to do then is we're going to take I have something again. I don't know, where did it go? Well, anyway, so it's around here somewhere. So what we're going to do is we're going to simplify things like this. We're going to go one at a time through here. And there is, when you're simplifying radicals with variables, it is so much easier than when you're trying to do all that numerical stuff yesterday. I say that, and I'll show you. They get a little mixed up. We'll get to it. We'll get there. All right. When I'm looking at one like this, when I'm taking the third root of 125y to the sixth, what I want you to think of is, well, third root of 125. Well, that's easy. What's that? That's fine. So I take care of the number first, and what I want to show you is what does the third root of y to the sixth mean in terms of exponents. In terms of exponents, this part means it's y excuse me, to the sixth divided by 3, isn't it? So how many times does 3 go into 6? Twice. What happens here is that you're going to use the idea of that nth root into exponents, because when you have exponents underneath the radical, that's the exact same setup as that. Your nth root becomes the denominator, the exponent is the numerator. So what you're doing is you're trying to see how many wholes can come out versus how many have to stay in. You're looking for remainders. What would change if I did, if this was to the 16th? Well, how many times is 3 going to 16? 5. It comes, 5 would come out. How many are left? 1. It's really quick, okay? Because you're looking at it in terms of, if you remember that when you're dealing with nth roots, your nth roots can be rewritten as fractional exponents, which there in turn turns into a division problem. And you're just looking at how many times something goes in there, what's the remainder, and that remainder stays underneath the radical, the nth root. It does seem like a lot at once. And it works the same if you're dealing with it, if they give it to you directly in terms of your exponents. I'm sorry, in terms of a fractional exponent. Half power just means square roots, doesn't it? Since I have the half power to a bunch of junk inside the exponent, I'm basically distributing that half power to every term. So 9 to the half, well, that's easy. What's that? 3. So here you get 3. U squared to the half is how much? U. B to the 10th to the half is B to the 5th. Okay. Exactly. That's exactly right. Okay. As you start walking through the exponent rows with these things, they seem like they're really messy, but it's not that bad. Okay. What changes here? Nothing. There's a z, there's a y, there's all this other stuff. You've done these problems before, you just haven't done these types of simplification problems with fractional exponents. So what do you think you have to do? Simplify. And remember, you never want fractional exponents in your denominator. That's kind of a rule, because that means you wouldn't have a radical in your denominator. So you would have to simplify as you go along, play war, do whatever. But as soon as you're done, you have to make sure that there's no fractional exponents in your denominator, and then you would do that whole rationalization trick. You know, add however many fractions you need to it. So if we have 6x y to the 1/2 over 2x to the 3rd z to the -5. As I'm writing this down, I could probably go ahead and say, oh, well, if I take care of my numbers first, that means I'm just going to have a 3 in my numerator. I have an x and an x to the 3rd. Who wins that battle of war? X. So what's a whole? Subtract a 1/3. 2/3, good. Y to the half, where does that stay or go? Does it do anything? And then z to the -5, where does that go? Goes up to the top. And then I could just erase my little thing or put it over 1, it doesn't matter. You're done. Okay. You're like, fourth root of the quantity x to the 4th over y to the 8th. You can write it as the 1/4 power, but it didn't spill though. Nice. Did it dent it? Nice. Good coffee mugs are where to go. Especially now you remind me, I should probably close my every time I. Now, if I think of this, remember, if you give you a problem with nth root, you leave your answer as nth root. If they give you a problem with exponent, you leave your problem as exponent. So if I want to, instead of rewriting this, Emily, because you were saying, oh, I go to the 4th power, do all that stuff there, whatever. Watch this. 4 goes into 4 how many times? 4 goes into 8 how many times? Was there any remainders? So I didn't have to worry about it. It's a great little trick. There's nothing wrong with going back to the exponent and rewriting it through, but remember, when you have an nth root, you're just saying, how many times is 4 going to 4? Once, so 1 comes out, nothing stays in. 4 goes into 8, twice. 2 come out, nothing stays in. If this was an 18, I'd say it goes in, 4 times? So 4 would come out, y squared would stay in. Because 4 goes into 18 how many times? 4. And how many? And that gives you 16, which means I would write it, if this was an 18, I'd say it'd be y to the 4th and then be the nth root, fourth root of y squared. And obviously I'd have to rationalize some stuff here, but that's what it would look like. Here's that same basic idea. I was just showing real quick about the remainder, how that works. We're going to do an example. I would have had to. That last one over there with this 1 and 7, we'll have to do that there. I was just showing real quick about the quick remainder thing. So if I have the fifth root of 5, and then a to the 5th, b to the 9th, c to the 13th, and I want to simplify out that root. First thing I try to see is, well, can I take the 5th root of 5? Nope. So as we go to simplify these things out, normally what I do is I move over my answer in case there's going to be stuff that goes to the left of the radical. I know that the 5 has to stay in. But what's the 5th root of a to the 5th? A. So when a comes out, a. Now here's that trick about the remainder again. Obviously when I said how many times does 5 go into 5, we said 1. There was no remainder. That's why 1a came out. How many times does 5 go into 9? 1. So I can take out a whole. How many are left? 5 goes into 13 how many times? Twice. How many are left over? 3. And that's your answer. Yep. Because what if you want to rewrite this in terms of the fractions and distribute and divide out, see when to left to go for it, that's fine. But I'm telling you, it is a great, nice little shortcut to rewrite it like that. Yeah, you're done. It's the end of the world. Okay. When I get to division problems, bless you. When I get to division problems, normally what I'll do is I will simplify, and then I will rewrite as a fraction. Because it's easier to work with the denominators as fractions. So, numerator, I'm going to have the cube root of x. Can't do anything about it. Denominator, 3 goes into 7. How many times? I get y squared, and then I get the 3rd root of y. Yeah. Because now I have this root in the denominator, which is bad. So I've always thought that when you're working with rationalizing, if you will, a denominator, it's usually cleaner to use the fractions as opposed to try to use end roots. Okay. So I would rewrite my denominator as y squared times y to the 1/3. And then just cube root of x right now. I need to create a whole in the denominator. How many more thirds do I need? 2. Okay. Y to the 1/3 times y to the 2/3 is y to the 3/3, which is y to the 1st. Okay. So this gives me y squared times y. I'm just writing long form here. Cube root of x, and then this is times the cube root of y, quantity squared. And now the only thing that's left for me to do is to rewrite the denominator as y to the 3rd. It's weird because it kind kind of forces you to switch around from time to time from both styles, from using both the nth root as well as fractional. Yes, sir. Different exponents, different bases. Okay? I can't combine those two because the y has the exponent of 2/3, whereas the x only has an exponent of 1/3. If they both happen to have a 1/3, I can put them in the same bracket. Since they have different exponents, I can't do that. A little weird. A little weird. Okay. Oh wait, we just. Yeah. I got this out of sequence. Oops, I corrected that. Close. No, we're gonna do more. Mass examples. That's great. same side. We'll do the odds again. Go 57.75. All right. Go odds again. 57.75. It's the same section, same stuff. It's just the next page over. And just go 57.75, and then we'll talk more about this tomorrow. It'll be the same stuff through. I'm trying to remember if I left I know the PDF file is on yesterday's calendar date. I'll make sure I put it on today's calendar date as well for you guys. But you just go back a day and be all right. We'll probably wind up doing some more of this tomorrow on a Saturday.